All right. We have the last F extensions today, and we need to get those done. Just a couple more, so shouldn't be too bad. Let's take a look at what we have. So yeah, so the other day, not yesterday, but the other day when we were streaming, we got through most of this stuff, like the fuse, multiply, add, and we did some of the converts too, but we did the first two converts, I believe. So let me see. Yeah, we did the first two converts, so let's just finish off. Did we actually add anything to the main part? Hold up, give me a second. Okay. Yeah, we need to add the converts to main. What are those like? Just destination register, RS1, alright. Destination register, RS1. Let's see what's so similar to that. I guess we can just take this. This would be conv int, and okay, so it was like a floating point number, right? So this would be an F, but this would be an X still. Destination register should be an integer one. And then let's do the next one too. The one for int conv fp. Alright, so for this one, alright, this one will actually take in different stuff. So I think it's like an integer register into a floating point register. Yeah, so this one will be X. And this one will be F. So it's just flipped. We need to see which ones. So now let's move on to, okay, so we did these two, so now we have to do FCVT, W, CVT, WU, right? Let's see. So that one has WS, LUS, SWU, SLU variants convert to or from unsigned integer values. Float to unsigned integer for WUS. Let's just make sure for sure, just to be sure. Let's just check this. So yeah, we did that one. Okay, WS, right? WUS. So we're converting a floating point number in a floating point register to a signed 32-bit integer. Okay, it's unsigned integer register though. Okay, I got that. Alright, let's do that real quick. So under decoder.h, so this will be what? Floating point to an integer, so it will be under the fp-conv int one floating point to integer register, so SCV TWS. we can copy that over to our encoder, put that in, it'll be in here. Let's see, scv w.s. w.s. So it's gonna be like that. Yeah, that is good. And okay, now we have to actually do the logic here. Maybe I should have done a couple of these. I kind of feel like I lost my flow a bit, but we'll get back to the flow. It's okay. Alright, so let's see. Let's go back. And let's see, FCVT-WS has an opcode of this value, and it's distinct. It has the same opcode value as the other two, but it's distinguished by a funct5. The funct5. Oh wait, the funct5 is actually the same. The funct5 is actually the same as this. So I think we can actually, okay. So opcode's the same as the SW one, right? So we can actually input that in. Wait, it's the same as the SW one? Yeah, it is the same. No, wait, no. I was looking at the wrong one. That's SW, but this one's the same as this one, so it's WS. The WS one. Oh wait, they're all the same opcode anyways. Doesn't really matter. The funct5 is the same. Funct5 is 0x18. But then it's gonna be int. It's gonna be like that, and then so it's gonna be further distinguished. So we'll say hold on. I see, so they're actually like that's actually very interesting. So they're actually using RS2 values as distinction. Okay, that's interesting. I didn't actually expect that to be the way that they'd actually do this, but okay, interesting. Okay, I guess what we can do here is do another nested structure. It's probably the best way to do it, so I don't have to like keep going for that. So I guess in here, for opcodes like this, it'll be if okay, we can instantiate rs2 in here. So inst rs2 is equal to get rs2 and then get the value. And if that's the case, we will have the if statement that fires. So if rs2 is equal to 0x0 for the first one, for this one 0x0, in that case, we will do all these instantiations here. And we can, looks like I messed up, hold up. Sorry, we have to move this here, up here. But let's just reverse everything we just did. I messed up for a second. Okay, let's reverse that. Okay, it's gonna be all here. This one's just gonna be WS instead, and then fpconf int. Yeah, that should work, and we can move this out. Else if the case of our index, the rs2 value being 0x1. So yeah, it's getting kind of, I wish they put it together, to be honest, instead of having one off and off. It's fine. Okay, so WS is the rs2 1, rs2 0, and then WUS is the rs2 1. rs2 1. So if that's the case, you can just take it from here, and yeah, you can just get that. You just get that value, and I think that's good. That's good for that. I think the best way is to just have this nested structure here. I don't think you can have anything else so far. Okay, we can just get rid of this for now. It'll be the same case here, I believe, with s.w. Let's just do that. Let's just instantiate that in, and that will be integer register, unsigned register to float. When we live, I was waiting the whole time. I just went live like 10 minutes ago, I believe. What's up, EXO? Alright, okay. S.W. Bro, I can't wait to be done with this part. I kind of want to just move on to the next part. How many do we have left? We got, okay, after this implementation, we have 1, 2, 3, 4, 5, 6. Yeah, still a good amount. It's fine. It's all good. We can speedrun. Okay, S.W, let's do it. FCT SW. So that's a different one. And in our decoder, that's gonna be up here. Change the game is probably going to be a liminal space / dream core mixed simulator game, or I'm going to keep it as it is. Alright, man, just remember what I told you the other day. You gotta at least get that idea down. At least the idea and the storyline. You don't have to like make it fully, but just like have an idea so like you don't get stuck. Have a good idea and make sure you can actually implement it well. Don't make it like, you can make it ambitious, but just don't make it too far out of your current skill level. But you can improve as you go and add more stuff. Okay, yeah. It's kind of just like with my project here. I started off knowing nothing about this stuff, and now I'm decent enough to do stuff on my own. SW, okay, perfect. And then they also have a distinction between RS2 and RS2 values. So I think that's pretty straightforward here. Just go down here and make the same if statement here, but just change the values. So it'll pretty much just be the same here. All the way up here. All this. So the funct5 is 0, 1, x1a, right? They have the same funct5 too, right? Yeah, they do. So yeah, they can be the same. So if that's the case, 0 is 1a, it'll just be changing the name. Same here. W. And also, this changes too. But delete the rest of this and then we're good. Okay. Or I could just mix both of their styles together. Maybe, if you want to. Just think about how they would flow together. Okay, yeah. I think that's fine. I don't really see any other better way of doing this. I think this is fine. And yeah. We can now go to the interpreter and actually do this. Alright, so for the case that this is WS, right, so what exactly are we doing? We're float to an unsigned integer, so okay. Alright, I got it. So we have a float here to an unsigned integer, but it's just going to be unsigned. That's pretty straightforward, to be honest. And unsigned. So we don't need to do the cast here. So yeah, that should be fine. Okay, yeah. And then same case with this. It's pretty simple, this part. This will be the SW. And this will be unsigned integer to float, right? Unsigned integer to float, so I think it's just better to copy that other one, to be honest. That's a similar implementation. So copy this. Alright, so unsigned, just change unsigned. Still static casting to a float though. And then yeah, I think that's it. Yeah, I'm gonna check now. I'm gonna check this now. Okay. Yeah. Okay, hopefully I get a perfect implementation here. For once, I just wanted to say, for once, thank you. I mean, that was pretty easy, so it's not really anything too crazy. Good instinct using RST to distinguish their variants. Yeah, that's exactly how the spec encodes them, so that's why I did that. Now the comparison instructions. Alright, let's try and do the comparison ones by ourselves first. I want to look at that. Alright, so wait, comparison ones. Oh, these ones. I'm gonna go in order, so I'm gonna get these next ones done. Sign injections. What? Alright, that's interesting. That's interesting. Not really a fan of them already, but is it this one? Sign, yeah, okay. Alright, so produce a result that takes all bits except the sign bit from RS1. The result sign bit is RS2's sign bit. Interesting. So we have a floating point destination register, floating point RS2, 31, and floating point register RS1. Interesting. That's very interesting. I don't know what I'm gonna do with that. Let's just start. So, okay, let me see what all these have in common. Takes a little bit, takes a sign bit. It's opposite of this. They're taking the same type, kinda. All of them are floating point registers anyway, so I think we can just store them as the same. Alright, what should I call them? I guess... How many are there? 1, 2, 3, just 3. Can I copy? Oh, okay. FC5, yeah, I thought so, but what should I call them? F sign? They don't. No, their format's different. It's not like... It's the same, right? It's not the same. Is it? Well, it kind of is, yeah. Yeah, it is. Never mind. I was wrong. I was wrong. He was right. Yeah, it can be under FPA then. Let's just initialize all of them. Oops. F, S, G, and J. S, and then we have F, S, G, and J. Oh, there's no N for that one. It's just, wait a minute, FS, okay, FS, G, and J, and S. Yes. G, and J, and S. Yes, and then the last one. FSG and JX. FSG and JX. Okay. Interesting. Okay, let's actually implement that. Still have an S until we've got, yeah. Okay. Hello, what's going on? Wow. I hate when this happens, dude. It's not even that error, it's just like she'll do anything dumb. Everything should be fine, dude. What is going on? Is that just like a bug? Alright, yeah, it's probably just a bug. I mean, we can test by actually putting it out. Wait. Alright, we'll take a look at that later, bro. I'm not too interested in that right now. I kinda just wanna get this done, bro. I'm kinda tired of this part, to be honest, dude. I'm definitely not doing the D instructions, bro. To be honest, I'll probably come back to it later. Let's take a look. So they have rounding mode. Let's see, 1010011. So they have the same opcode, I believe, as the integer ones, right? 101001. Yeah, they do. Yeah. Okay. One zero one zero zero one one. So that's hex 53. So hex 53, and they're distinguished by their func5 and also their rounding mode. So let's see, func5, they all have the same func5, which is 0. That's a 4 in hex, I believe. You can just check that. Yeah, it is. Okay. Yeah. So distinguished directly by their rounding mode. So it depends on what their rounding mode is. So yeah. So the first one was 000, I believe. And implement the values. All right. So they need pretty much the similar amount. So they just need these we can copy over, but they also need install rs2. Initialize it there. Okay. And what else do they need? So the rounding mode, rs1, rs2, rd, and yeah, I think that's it. Yeah, that's it. We can do the same with others. Just their rounding mode separate. Oh yeah, I forgot one more thing. Hold up. Their name and their type. Yeah, so their type will be FPA and instruction name. Okay, this is such an annoying name to type out. FSGNJ. S, yeah. FSGNJ. No, it's not NS, it's S, just S. FSGNJS, yeah. Yeah, and then same with this. Rounding mode's gonna be 1 though, I believe. Yeah, rounding mode, that's the one with J and S. So just copy that over. JNS. It's pretty much the same there. And then the final one. What would I do? Hold up. Alright, okay. Alright, that's good. And then this one is X, I believe. J-axis, yeah, J-axis. And yeah, it's the same, but rounding mode is 2. Right? Yeah, it's 2. Okay. Now it's implemented in the interpreter. And FSG NGS. Alright, case instruction. Alright, so let's actually look at what it does. So produces a result that takes all bits except the sign bit from RS1. So first we need to actually take the bits. Okay, let's set up our variables. So it's gonna be a float for the RS2. I believe, right? Let's see. It should be a float, so yeah, floating point for RS1 and RS2. Get the read match first, and it'll be a floating point register, not the integer one. So it's .rs1. Back, I was bored, and also I'm not able to work for now, but I'll be working soon. But as of right now, I can't. Why can't you work right now? What happened? Same with our RS2 value. I'll just copy this over. Yeah, okay, that's good. Now we need to extract the bits from them, so produce a result. Okay, so we know we're writing, right? We know we're writing, so we're gonna need to write the floating point register either way, and I'll take it is.rd for now. We'll just keep that there for now as 1. But now we need to actually write the part for taking the sign bit. So we actually need to extract the bit. So RS2's sign bit. Okay, so taking all bits except the sign bit from RS1. So RS1 has 5 bits. Sign bit. So I'm guessing that's the 5th bit right here. So we need to AND it and take in. So when we AND that number, it would end up being this, preserving the 5th bit and taking that. So I believe it's X10. I'm not actually sure, to be honest, but let's just give it a shot. Let's just try to see if that's the one. So we can take our, let's just call it value. We call it float value, and let's just say it's dot, not it's dot. We already have rs1, and ANDing that value with x10, I believe, or I don't know. We can't do that. Hold up. We actually can't do that, so how do we go about doing that? This needs to be an int value. But we need to static cast this to an int first, or what? Oh, we don't want to do that. We don't want loss of precision there. We definitely don't want to do that. I actually don't know, to be honest. Let's check on here. I believe you put it up here, right? Okay, let's see. Wait. Wait, what is that value in hex? Let me see. Oh, yeah, hex definer. Okay, oh, it's doing all the 32 digits. And then for this one, what is going on here? That one's also 32 digits, but it takes every single bit except sign bit. Okay, so the bits from RS2 isolates everything except the sign bit, so taking that bit 31 and just fix bits 32 there. Oh, I thought it would just be the 5 bits. I didn't know it was all the bits. I didn't know it was all the way up to 32. Interesting. I think I can give it a shot. Let me just go up here for a second. Give me a second. I see. Will be signed integer. Yeah, no, it'll be unsigned. And wait a minute. And we do have to read the word too, yeah. Reading the memory, wait. So well, we don't actually need the immediate here, so okay, I'm kind of confused. Wait, so we still need to start off with the float, so I think this is fine to keep it as that. But we do need to convert them to raw bits now. So that's when we'd use we'll call it like bit 1 and use that. This is memory pi. Alright, so we're trying to copy that to that, so okay, so the address of bit 1. I want to take the address of now the thing that we're copying from rs1, so put too much, and then storing that with the size of bit 1, I believe. Or call it rs1. Same with these. Just do the same for the second one. Wait, that's wait. No. We need to instantiate its value now. Hold up. That's what we did wrong. Just yeah. So that will stay. We'll copy it into value. We'll copy it into value, so it should be here, like this. Probably this is wrong anyways, but we just gotta give it a try at least. And it should be size of value. Right, so now, so we converted them now into the proper unsigned integer version. Now we can extract the bits, I believe, so. So we want to get. Wait, I'm actually. Let's check this. What did he do? Oh, he just put it back into result of the 2 bits. So grabbing the 31st and then 30 to 0. Okay. And just store that in. So okay, that makes sense. That makes sense. And just change that. Yeah, this is definitely wrong, bro. But let's just see. And then, yeah, he's definitely gonna say it's wrong. But let's see how close we were at least. Separate variables. Oh, okay. Yeah. So we'll call this value. Well, yeah, I guess we can just call it bits, right? Just like how we did bits 1, bits 2, and then copy bits 1 right over here. And then this one will be bits 2. One. Oops. Alright, wrong bit manipulation. Okay, let me copy this now. See if it's better. Okay, still have to do something back. Yeah. Float, not. You have to map result back to float. Yeah, I forgot about that. Actually, our implementation wasn't too bad. It wasn't too off. It was actually pretty close. I just forgot that I need to separate them. It's not too bad. It's not too off actually. So we just needed a bit more of that. Yeah, let's store it in a float. So let's call that float f, or yeah, we can just call it float f. So just initialize that. And then instead of mcpy it back. So address of f, address of results, and then size of rf. And that should suffice. And it should be our f value. Yeah, okay. Not actually too far off, to be honest. Oh yeah, break. Totally forgot. Yeah, alright, now it's good. Put the break statement. Okay. Okay, now we have to do the rest of the implementations. Let's actually go over this first before. Alright, so what it said was we're producing a result that takes all the bits except the sign bit from RS1. Result sign bit is RS2 sign bit. So here, taking RS2, just the first bit. So that's why we're ANDing it with 0x, that number, which takes just the 32nd bit, the 31st bit, and then has that at 1 that preserves that bit, and then zeros every other bit. And then here it's the opposite, where we have the sign bit as 0 and every other bit is preserved with 1s. And of course we have to read from the register to get the value, and then converting that into unsigned integer to get the bits, because we can't do that. We can't get float bits. So we have to cast that properly. Then here, yeah, then here we got that, and then casting that result back to float, since we need to write to the floating point register, not a regular integer register. I do have one question that I'm going to ask. Yeah, so we'd lose precision if we made it a static cast. To preserve the exact bits. Alright, I think I kind of understand the difference now as to our implementations. Alright, let's get to the next part. JN.S, I believe. FSG and JN. JNS, and then we'll have this. Produce a result that takes all bits except the sign bit from RS1. It's the opposite of that bit, so okay, interesting. So it's practically the same thing, but there's going to be one difference. We're still taking the floating points and all those, but here's where it's a little bit different. It's the opposite of RS2 sign bit. What does that mean, the opposite? Did Cloud give any hints? Negated sign bit from RS2. How do you flip bit 31? I mean, flip is always XOR, I believe. Right? Because there's no actual like negation thing in C++, I believe. I'm not actually sure, but I think, yeah, I think we need to do XOR. XOR of that, I believe. Flip. Yeah, that's right. And then we need the last one. What's the last one gonna be? JXS. JXS, and then, okay, let's see what it does. Okay, so JXS produces a result that takes all bits except the sign bit from RS1. The result sign bit is XOR of the sign bit of RS1 and RS2. Hey, what's up, somebody, some? Interesting. Very interesting. Interesting that you're here. Okay. Okay. Alright, let's keep moving forward with this. Alright, so we have FSG and JX. Alright, produce result takes all bits except sign bit from RS1, so we have that done. But now we need to get the RS1, the 31st bit, and XOR that with the 31st bit of that. So I guess it just would be an XOR, right? But how did he do like an XOR full XOR, or you can just do XOR of those bits like that? Okay, interesting. So XOR these two and then XOR, I believe. Let's see if that's correct. Or wait, it wouldn't be XOR. It'd be AND since we're masking it out. Yeah, he's probably gonna tell me the same thing here. Yeah, it's AND. Yeah. Alright, so we got that. Alright, yeah, that's good. That's pretty good so far. And then we need to actually it's already implemented, so that should be fine. We don't need to implement it in here. But yeah, we need to move on to the next part. Okay, let's try and move on to the next part. which will be fmove. So it moves the single precision value in floating point register 1 according to the lower 32 bits of integer register RD. Are not modified in the transfer, and in particular, the payload of non-canonical enums are preserved. Okay, so in this case, we need stdmemcpy. We don't want the bits to be modified, so we want to preserve all the bits. So we need to use stdmemcpy. Moves a single precision value code to lower 32 bits of integer register RD. So these are pretty similar in how they're implemented. It's going to be in an integer register RD, and this will be in a floating point register RD. So does it mimic the other ones from before? The conversion, it kind of does, yeah. Like the way they're implemented, RS1 RD. It's the same here, so we can actually implement them the same way. Just in here we have to change. So floating point to integer register, it will be fmv x w, and same here. Well, it'll actually be here. This one will be integer register to a floating point, so we'll have integer to floating point. So what was the name of it? fmvwx. Yeah, that's good. In our decoder, we can just implement xw fmv.x.w, and then here integer register, it will be the same, just switched around. X. Yeah, that's good. And we can implement it in here now. We just got, we're on the home stretch here with these last couple ones, and we can move on. Next stream, I'll try and start to get into pipelining with the data path and control. We'll try to get that done. Well, not done, but we'll try to get that started. Moving to pipelining tomorrow, so we just gotta finish off these last couple floating point instructions around the home stretch here for that. So yeah, let's do it. All right, okay. Let's see how they're decoded. So their funct5 is distinct. That's a good sign. Yeah, that looks to be pretty good. So their funct5 is distinct, so we can distinguish them by their funct5. I think that's good. Their opcode, let's check what their opcode is. 10100011. Opcode 53. So they're the same as those ones. I just want to check if anything like overlaps. Just want to make sure nothing overlaps. Yeah, no, I don't think anything overlaps. Yeah, yeah, we can implement now. So opcode is 53, and then their funct5 is going to be distinct. First one is going to be 1C in hex. Interesting. 1C. And we don't need any other distinction, I don't think. I think that's the appropriate distinction. see what the name was again. FMB XW. And this will be under fpcon bit. Yeah, that's good. Alright, has everything. RS1, RS2, RD, and FMT. Yeah, that's everything. Okay. Same here, but their opcode, their font file will be different. So WX is 11110. Okay, that's gonna be 1E in hex. 1E in hex. And we switched, and this will be integer to floating point register, and everything's the same. All right, implementing now the interpreter. All right, let's see. So it's going to be a quite a different one. Shouldn't be too bad. Let's give it a shot. So for the case of FMB XW, let's see where that is in here. FMB XW. Alright, so for that one, the single precision value and floating point register RS1 represented in actually going to the lower 32 bits. Alright, so we need to grab those bits first. So let's try and do that. So let's just get a float RS1, and we can read our floating point register for RS1. Just like we usually do, and now we can set an unsigned int value for our bits, and we can call that. We can just zero initialize it, and now we need to. Pretty much the same thing up here, but I'll just try it out again for practice, because we are encoding this time for bits 31 to 0, so all the bits. So we don't need to mask anything this time. So yeah, we can store the bits, the address, and then stored from the address of RS1 and size of our bits. Okay, that's good. Alright, so now we're taking. Okay, we already have bits 31 to 0, so we need to sign extend. Now we need to sign extend that though. Did we ever do that in any place before? Doing a sign extension like that? We are writing to an integer register, I believe, right? Yeah, integer register RD. Okay, with the sorted result. Okay, how do we want to do this? I mean, I think we already have it just with that, right? I think we'd literally just write bits. I think it's literally just that. And break statement. I mean, it should be. I don't really see what else we can really do there, because it should already be in place from bits 31 to 0. And I'll also give these two. Okay, so it was right, yeah. I was overthinking it. We don't need anything else. Everything should already be in place since we copied it over properly. So, all right, yeah. This should just be simple. Should be WX, and this is gonna be. This one was float to integer, so it's gonna be integer to float. So it'd be the other way around. Is it signed? Give me a second. Let's find it. WX. Enter register rs1. Yeah, it looks to be. No, it's not signed. I think it's just unsigned. Does it usually specify when it's signed? Let's check if they usually do specify. Yeah, they usually do specify, so they didn't, so it's just gonna be unsigned as usual. Yeah, it's gonna be unsigned. Okay, regular register. We'll also call this bits as well. It should be the same here. It's just we're changing it. This will be float actually. Float. And we're writing to a floating point register, so it'll be this. And yeah, we can show that over. Yeah. Okay. That's good. The last couple ones we have floating point compare instruction comparison. So we have the equal, less than or equal to, and then I don't know what this is, but we'll check it out. This one seems kind of complicated, but we'll see when we get to that. Let's just finish out these three. All right, so these ones take in RD, RS1, and RS2. They follow a similar pattern to the arithmetic instructions, so I guess we can store them under arithmetic. Just want to make sure real quick they're not stored in integer though. Oh no, they are. They are stored in integer registers. Yeah, so the RS1 and RS2 are floating point, but then they're stored into an integer register, so we can't reuse arithmetic one. Yeah, I think, yeah, we can't, we have to make a new value. Right, we'll call it, I want to make sure how many we need. So XFF, XFF. Okay, we can have one then. They're all the same. We could just have one register. Not one register, I mean one instruction type. And we can call it fcomp for fcompare. Right, yeah, that's perfect. And we'll store it under here. Floating point comparison instructions, and we can add the ones that we're adding in. So FAQ, FOT. Oh wait, this is the wrong one, right? Oh, wrong ones. I scrolled down too far. We want the S ones. FAQ.S. Either way, it's the same thing, so it's fine. It just the suffix is different. FOTS and FOES. Alright, yeah, let's do it. Server decoder. FAQs. And then basically just copy the rest. FLS, and then FLE.S. FLT, sorry. FLT. And then it's FLE, yeah. Okay, that's perfect. And yeah, go to the decoder part now. All right. Okay. What are they distinguished by? They're distinguished by wait, actually that's interesting. Hold up. Oh wait, never mind. They just formatted it a bit different here. Okay, I see. It's the same. Alright, func5 is the same, but they're distinguished further by their rounding mode. That makes sense. Okay, so their rounding mode is different, so their opcode's all the same, I believe then. Yeah, let's alright, yeah. It should be hex 53, looks the same as the others, hex 53. So let's see. Not func5. Let's see their func5 value 10100 x14. And in that case, mode. 0x2, I believe, for the first one. Yes, 0x2. And we want to change these, so it would be FEQ. Oops, FEQS. And then this will be comp. RS2, RS1, RD. Looks to be the same. Looks to be the same. They all have that. Now it's just gonna be the same. RM is 1. And the RM should be 3 here, or what? No, it should just be 0. FLE. 0x0. Okay, that's good. Now we can do the implementation. Okay, that's good. Let's see what to do. Alright, so FEQ.S from the quiet equal comparison between floating point registers RS1 and RS2 and record the Boolean result in an integer register RD. Interesting. Okay. Give me 1 second. Just want to take a look at these ones. Just to get an idea for a second. Okay. I think I understand. Oh, where did it go? Alright, here. So let's just establish our RS1 and RS2 values first. So both be floats. And because of that, we have to read from the float register. And instantiate. Both instantiated properly, and then we need to do a comparison operator between those two instead of an integer register. So we're reading to the register, just a regular register. And also, we want to static cast these. Well, first, no, wait. We'll static cast the end. We first want to do the interpretation first. We'll call it float Q, and then do the comparison between these two. Wait. Are you even able to do that? I guess you can. Alright, then that's fine. Sorry, so RD, and we want a static cast, so static cast. So this should not be a float, then it would be a Boolean. Not Boolean. A static cast of that EQ. What does that mean? Wait, hold up. Too many arguments. function call. Did we mess something up or? It should be that, no? I mean, too many arguments. Not. I swapped. Accidentally swapped two words. Wait. Wait, I was looking at the wrong one. I was looking at this one. This one needs to be. Yeah, but that still doesn't fix this issue, so I went wrong. Oh, I see. Wait, okay. Oh, we used the wrong thing here, dude. Silly mistakes. No wonder. Okay, but why do we need it to do it like that instead of just having that? Let's see if there's something different. Okay. Alright, so my version's also fine. The break statement. Can implement the rest. Yeah. So it's 0 higher operations. Nan. I think he said it's too close to already returns false for NAND comparison, so you actually find there. And yeah, I think we should be good. Correct. All of the comparisons look good. Like writing NAND handling works automatically through C++ flow comparison semantics. Okay. Let me just check, because there's one more. F class. Let me just ask if that's necessary. Actually, is F class in here? Let's see. There is one. Sounds strict and it's actually fun to implement. Terminate mask by checking each condition and setting the corresponding bit. I mean, I guess we gotta do it, guys, right? Like, it wouldn't be right if I just stop at the last one, even if it's hard. I guess I gotta do it, right? Alright, we got one more left. Let's just finish that one and we're done for that. And we can start pipelining tomorrow. And other stuff. So yeah. Alright, let's finish the last one out. Alright, this last one, what does it print out? It doesn't print out anything? Oh no, it does. Oh yeah, it does. F class RD RS1. What is it storing? So floating point register and writes to integer register. So it technically counts as a floating point convent. So I guess yeah, I can implement that in here. Okay, alright. Yeah. Let's see. It should count as this class. Class.s. So it's gonna be 3 S's. And implement that in here. Okay, that should be good. F class of S. Alright, so this one will be the last one. We'll end up the stream, guys. That means we'll be done with these floating point instructions after this. So what's it distinguished by? So it's distinguished by funct5 is going to be 11100. Well, let's check the opcode first. 1010011 is the same as the rest. 1010011. And this is 11100. Let's see. Funct5 of 1C. I'm pretty sure we had that before. Yeah, funct5 of 1C we did have here. So I wonder if some might overlap accidentally. But it should be fine. I guess the rounding mode we can do X1. So in here, class, and then, oh wait, that's right, FP convent. In here, it should be RM, and we'll get 0x1. I think it's fine. That's good. And then the same RS2, RS1, RM, RD, FMT. Yeah, that's good. Implementation now in here. Let's see. So it's quite a lot of implementations here, so that'd just be like a huge chain of ifs or something. Oh, okay, Claude's just giving it to me. Interesting. Let's read it though. Wait. Mask or equal to? Wait. So, alright, that's fine. That's fine. I get that, but okay, let's look at the mask properly. Wait, the mask. Okay, each one shifted by each bit. Okay, I see. Left shifted by each bit. And in the case of each one, so it's negative infinity, negative number, negative 7 on a number. Oh, is that literally just it? FP classify, FP classify. Yeah, I was probably never gonna get this implementation, to be honest. But yeah, we can implement it into our code. There's no point of writing it out, to be honest. It's infinity. And I guess FP subnormal is already like a hard-coded variable itself, a hard-coded constant value or something. Negative mask. Okay. I need to understand one thing though. Why do we write it like this? Oh, compound assignment operator? Okay. I actually didn't know that, to be honest. Mask equals mask or... Oh. Okay, I was wondering what's going on because that didn't look like proper implementation. I see. Okay, now that makes sense. I was wondering what was going on with the syntax there, but yeah, that makes sense. But I guess, yeah, we are pretty much done. We are pretty much done with the implementation of F-type instructions. We are pretty much done here. Let's just send it over to Claude, make sure everything's good. Also correct, physical not activity looks good. One thing worth noting, bit 8 signaling not a number is left unset. only setting bit 9 for one end. Okay, decoder. Yeah, we do have a get arm function, it's fine. Yeah. Okay, I mean, decent code base so far, to be honest. It's a lot. I'm not gonna lie, it's a lot, dude. 800 lines. It's actually ridiculous. But once we'll refactor later, to be honest. 800 lines for the decoder. We got like 500, almost 600 lines for the interpreter. Oh, interesting. Okay. Yeah, I think we're done today. We'll see what we can move on for this project, and yeah.